At the beginning of section 5.2, we observed that if the graph of a function f is viewed as a two-dimensional mountain range, then the relative maxima and minima correspond to the tops of the hills and the bottoms of the valleys. That is, they're on the high and the low points in their immediate vicinity. In this section, we will be concerned with the more encompassing problem of finding the highest and lowest points over the entire mountain range. That is, we'll be looking for the top of the highest hill and the bottom of the deepest valley. In mathematical terms, we'll be looking for the largest and smallest values of a function over an interval. Definition 1. A function f is said to have an absolute maximum on an interval I at a point x0 if f of x0 is the largest value of f on the interval I. That is, f of x0 is greater than or equal to f of x for all x in the interval I. Similarly, f is said to have an absolute minimum on I at the point x0 if f of x0 is the smallest value of f on the interval I. That is to say, f of x0 is less than or equal to f of x for all x in the interval I. If f has either an absolute maximum or absolute minimum on I at x0, then f is said to have an absolute extremum on the interval I at the point x0. There is no guarantee that a function f will have absolute extrema on a given interval. Let's look at the following three examples. For the first graph, this function is defined on the entire real line from negative infinity to infinity. Notice how the function continues downward until it reaches an absolute minimum point. There is no point lower, so this is considered an absolute minimum. It then begins to increase and continues on upwards to infinity. These points right here are not relative extremum because, again, this point right here that my cursor is on is not even a maximum because there's a point later which is higher than that. So there are no dips or valleys here. Even though it has a wavy appearance, it doesn't have relative extremum along the way. They just continue to go up. Same thing on this side. So this function has an absolute minimum but no absolute maximum on the open interval from negative infinity to infinity. This is the interval I that we're talking about. So in this case, the interval I is the real line. For the next graph, this function has no absolute extremum at all. It just continuously is increasing, and there is no point that is absolute maximum or absolute minimum. So there is no absolute extrema on the open interval. Finally, for the third one, this function has an absolute maximum here and two absolute minimums here because they are the same height. If one was lower than the other one, then that would be an absolute minimum, and the other one would just be a relative minimum. This one has its absolute extremum on the open interval from negative infinity to infinity, meaning that no other maximums or minimums absolutely occur on the entire interval. Now let's look at the next example. The next example has a finite open interval. It's finite because it only goes from A to B. It's open because it doesn't include A or B. Now, this function does have absolute extrema on the open interval. It has an absolute maximum at this point here, and it shares two absolute minimums at these points here. Now, again, if one of these points was lower, then that would be the absolute minimum, and the other one would not be absolute. It would just be a relative minimum. So this has an absolute maximum and minimum on the open interval from A to B. Let's look at the second example. In this case, f has no absolute extrema on the open interval from A to B at all. It doesn't include the endpoints A and B, but it is a finite open interval. It has two vertical asymptotes, and notice the function is always decreasing. It's always going down. And so there are no absolute extrema on this interval. Finally, the third example f does have an absolute maximum and an absolute minimum on the closed interval from a to b. Again, we'd say that that interval is finite because it begins at a, it ends at b, but in this case, notice it has the endpoints. So it turns out that the absolute maximum is at b, and the absolute minimum is at a. And this can happen quite often. Sometimes you have to inspect the whole interval, specifically if you're including the endpoints, because even if you have a maximum or a minimum inside the interval, the absolute maximum or minimum may actually occur at the endpoints. So you need to make sure you do that by inspection. Okay, the remainder of this lesson will now focus on the following problem. So the problem is two-parted. A, determine whether the function f has any absolute extremum on a given interval I, and B, if there are absolute extrema, determine whether they occur and what the absolute maximum and minimum values are. That's going to now take our attention for the remainder of the lesson. Here's the first example. Does the following function have any absolute extrema on the given interval? Now the interval in this case is from 0 to pi, and notice it's an open interval, so it doesn't include the endpoints. This would be our interval I. So what do we do in order to figure this out? Well, one thing we can do is just use our technology in order to graph the function, and then do it by visual inspection. So what I've done is I've taken my calculator, and I've placed in tangent of x minus pi over 2. My window, I've made it go from 0 to pi, the open interval. I've decided to let my y minimum go from -20 to 20. You can have different y values. Now you do need to make sure that your calculator is in radian mode. If you don't, then you're going to get an incorrect graph. I'm going to hit graph, and so now I look at the following function. And I notice that there does not seem to be any absolute maxima or minima on the interval. As a matter of fact, it looks like from 0 to pi that those are two vertical asymptotes. And so the answer to this question is no. This function does not have any absolute extrema on the given interval from 0 to pi. Does the following function have any absolute extrema on the given interval? F of x is a linear function, mx plus b, 2x plus 1, and x is on the closed interval from 0 to 3. This means that it includes the endpoints. So we graph it, we inspect it graphically, and we notice that since it's a linear function and since the slope is positive 2, it's an increasing function, which means that the absolute extrema have to exist at the endpoints themselves. So the answer to this question is yes, it does have absolute extrema. It has an absolute minimum at 0, and it has an absolute maximum at 3. Notice that when I say it has an absolute minimum at 0, I'm talking about the x value, not the y value. And notice when I say it has an absolute maximum at 3, again, I'm talking about the x value, not the y value. If you ask me what the absolute maximum is, well then I would say the absolute maximum is 7 at x equals 3. And so what an absolute maximum is and where it's located are two different questions. So you have to be careful about what's being asked of you. If the question asks you what the absolute minimum is, well, look at the graph here. What is the absolute minimum? Well, if you said 1, you're correct. But if it asks you the question, where is the absolute minimum located? Well, then it's at x equals 0. So the answer to this question is yes, it does have absolute extrema on the closed interval from 0 to 3. The extreme value theorem. If a function f is continuous on a finite closed interval from a to b, then f has both an absolute maximum and an absolute minimum on the closed interval from a to b. Returning to our previous example, this function was guaranteed to have absolute extrema on the closed interval because of the extreme value theorem. It's a closed interval from 0 to 3, and all linear functions, mx plus b, are continuous. And so by the extreme value theorem, this was guaranteed to have an absolute extrema on the closed interval. It just so happened to turn out in this case that the extrema occurred at the endpoints themselves. Theorem: if f has an absolute extrema on the open interval from a to b, then it must occur at a critical point of the function. Let's consider the following example. This function is continuous and the interval is closed because the endpoints are closed points. So by the extreme value theorem, there must be absolute extrema. And visually, by inspection, we can see from the graph that these extrema occur at the endpoints themselves. So these would be considered the critical points, the endpoints themselves. The absolute maxima is at B, and the absolute minimum is at A. Our next function is also continuous, and the interval is also closed. So by the extreme value theorem, there must be absolute extrema. And we see that visually, except this time the absolute extrema do not occur at the endpoints. They're intermediate between the endpoints. There's an absolute maxima at this point, which we'll call x0, and even though it's not in the graph, there's an absolute minima. I'll call this point x1. And so the extrema exist within the closed interval. So an absolute maximum occurs in the open interval from a to b, at the point x0 where f prime of x is equal to 0. Now we haven't talked much about that, but that's where the slope of the tangent lines are 0, and that helps us identify where extrema occurs. Another problem with this visual example is that this is talking about the open interval, but graphically here we're looking at closed endpoints. So the graph here doesn't quite match what the box is talking about. So let's just consider this interval to be closed, and so we'll make this the closed interval from a to b. So why is the tangent line so important? Well, notice that visually we can see that there's a relative minima here, a relative maximum here, and an absolute minimum here. Now if I let the tangent line continue along and progress along the curve, I notice that when the tangent line is actually equal to 0, when the slope of the tangent line is equal to 0, I have achieved either a relative minimum or an absolute minimum. I continue along the tangent line, and then the tangent line slope becomes 0 again, and so when the tangent line slope is 0, I have either a relative maximum or an absolute maximum. Continue again, and then we achieve, hopefully, if I can, there we go, the slope of the tangent line 0, and this indicates either a relative minimum or an absolute minimum. Now, how do I know the difference between it being a relative or an absolute? Well, that happens by inspection. We look at it graphically, and then we can say from the visual, hey, this thing is smaller than anything else. So that's what would make this an absolute minimum. So the first derivative is very crucial and can be a wonderful tool in figuring out where absolute extrema occur. Now the exciting thing is that when f prime of x equals 0, we have a possible point of extrema. But the trap that Calculus 1 students fall into is assuming that just because f prime of x equals 0, then that absolutely has to be a point of extrema. And nothing could be further from the truth. You don't necessarily have an extreme point just because the slope of the tangent line is 0. And here's an example. So what I'm going to do is I'm going to show you the points of extrema. One is located at negative pi, 0, and pi, and I let the tangent line continue along. And it turns out that when the tangent line here is 0, that f prime of x is equal to 0. But this is not an extrema point right here. This is neither a maximum nor a minimum. So it is possible to get a tangent line with slope 0 and not have it be an absolute maximum or minimum, or even a relative maximum or minimum. It could just be continuously be decreasing or continuously be increasing there, and the slope of the tangent line is just 0. Now for this particular function, we do have an absolute minimum at least, and that occurs at 0 itself. And so we do have an absolute minimum. But the other 2 points are neither points of extrema points of maximum or minimum. They're just places where the tangent line happened to be 0. So don't fall for the trap that simply says just because f prime of x equals 0 that you must have a point of extrema. You won't know that until you inspect the graph. Now we look at this continuous function, and we notice that it does have an absolute maximum on the open interval from a to b. Even though the picture says it looks like a closed interval, for this example we'll just consider the interval open. However, notice that the place where it has its absolute max is a point of non-differentiability. The derivative does not exist at the point x0. That means that the limit as x goes to x0 from the left of f prime of x does not equal the limit as x goes to x0 from the right of f prime of x. So the limits for the derivative from left and right do not agree. Therefore, the function is not differentiable. But just because it's not differentiable doesn't mean it's not in a point of extrema. As a matter of fact, it is. So extrema can happen even when you can't differentiate the function at a specific point. You've got to be careful. The first derivative is only a tool to help us understand where extrema can occur. But just because we can't take the derivative doesn't mean we don't have a point of extrema. And that's where you have to be a little bit careful. So okay, the absolute maximum occurs in the open interval from a to b at a point x0 where f is not differentiable in this example. Have you ever heard the saying, the best way to learn how to fish is just to fish? Well, the 1, 2, 3 procedure I'm about to show you is teaching you how to fish. I'm now going to give you a procedure, steps 1, 2, and 3, how you, the student, can find points of absolute extrema of a continuous function on finite closed intervals. The first step is just to find the critical points of f in a to b. How do we do that? Well, we find out where the derivative is equal to 0. That's a potential place of finding critical points. Step 2, evaluate the function at all the critical points and at the endpoints. Step 3, the largest of the values from our second step is going to be the absolute maximum, and the smallest is going to be the absolute minimum. So we're going to do this in the next example. Find the absolute maximum and minimum values of f of x equals 2x cubed minus 15x squared plus 36x on the interval from 1 to 5, closed interval, 1 to 5, and determine where these values occur. Step 1. Find the critical points of f in the open interval from a to b. So we take the first derivative of f, and we get 6x squared minus 30x plus 36. Next, we set this derivative equal to 0, because again, we're interested of where the tangent line slope is equal to 0. This function has a common factor of 6, so we divide through everything by 6, and we get x squared minus 5x plus 6 equals 0. Thankfully for us, that quadratic equation factors easily. X minus 2 times x minus 3 equals 0. And so using the zero factor property, we get the two solutions 2 and 3. Both 2 and 3 are inside of the closed interval. So now what we have to do is we have to test both these points and the endpoints to see which one's the biggest and which one's the smallest. We then go ahead and plug all of these points, both the critical points of 2 and 3 and the endpoints of 1 and 5, into the function. The biggest one is f of 5. We get 55. So that's the absolute maximum. The smallest one is 23, and that's at the other endpoint. And so we end up getting the absolute minimum is 23 at x equals 1. Next, let's go ahead and look at the function graphically. Notice what we get graphically. This is a relative maximum at 2, and this is a relative minimum at 3, but not absolutes. The absolutes occur on the closed interval. At 1 is the absolute minimum, and at 5 is the absolute maximum. Now in this case, for the graph, the absolute maximum kind of goes off the graph a little bit. I'd have to scroll that up until it gets to the value of 55, and I'll go ahead and do that. So there's the value of 55, and this happens when x is equal to 5. And so this is why inspection is very critical. Let's now discuss some general conclusions that we can make. What if we know that if we take the limit as x goes to a negative infinity of the function, we get positive infinity, and we also know that if we take the limit as x goes to positive infinity of the function, we get positive infinity. In other words, the end behavior of the function is both positive infinity in both directions. Well, a conclusion that we can make, if f is continuous, of course, is that f has an absolute minimum but no absolute maximum on the open real line from negative infinity to infinity. So the graph would look like something like the following. Okay, well, what if the limit as x goes to negative infinity and positive infinity both yield an end behavior of the function going to negative infinity? Well, the logical conclusion is, if f is continuous, is that f has an absolute maximum but no absolute minimum on the open real line. And so the graph may look something like this. Now, what if we have differing end behaviors? Meaning, as x goes to negative infinity, the function goes to negative infinity, As x goes to positive infinity, the function goes to positive infinity. Well, the conclusion, if f is continuous, is that f has neither an absolute maximum nor an absolute minimum on the open real line. Notice absolute is the key here. It may very well have relative minimums and relative maximums. The graph may end up looking something like this. Finally, if we just switch that end behavior and let the function go to positive infinity as x goes to negative infinity, and x go to positive infinity as the function goes to negative infinity, if we switch that end behavior, we end up with the same conclusion. F has neither an absolute maximum nor an absolute minimum on the real line. Again, this doesn't deny the possibility that it has relative maximums or minimums, only absolutes. The graph may look something like this. Now, after looking at those 4 examples, the question now is this. What can we say about the existence of absolute extrema on the real line for polynomial functions? You remember that polynomial functions are some of the nicest functions to differentiate because we only have to use the power rule. So, if p of x is a polynomial of odd degree, let's just look at that. If it's an odd degree, then it has differing end behaviors, meaning one end is going to go to positive infinity, the other end is going to go to negative infinity, the functions are. So they're going to have opposite signs. And that immediately means that there's no absolute extrema for polynomials of odd degree. But if you take even degree polynomials, then their end behaviors are exactly the same. Either it will both go to positive infinity on both ends, or negative infinity on both ends. Well, let's say that the leading coefficient, if the leading coefficient is positive, then the limits are both positive infinity at the ends, and there must be an absolute minimum. But if the leading coefficient's negative, and the power is even, the degree of the polynomial is even, then the limits, the end behaviors, are both negative infinity, and therefore the polynomial must have an absolute maximum. So we can make some general conclusions about polynomials, which is very nice. Rather than having to do a whole bunch of work, if we know it's a polynomial, if we know what the degree is, and if we know what the leading coefficient is, we can make some general conclusions about whether there's absolute extrema or not. Determine by inspection whether p of x equaling 3x to the 4th plus 4x cubed has any absolute extrema. If so, find them and state where they occur. Well, this is going to be easy. P of x is a polynomial. Not only that, it's even. So the end behavior has to be the same on both ends. The leading coefficient is 3, which is positive. So that means that the limit in both cases as x goes to negative infinity and positive infinity is positive infinity. So this function goes up at both ends, which means that this polynomial absolutely must have an absolute minimum. Now we take a look at the graph, and our graph just verifies what we've already concluded. So we absolutely must have an absolute minimum, and it looks like we do have one. Now graphically we can kind of look at it and say, well, it's at -1, right? But we need to do a little bit of mathematics just to verify that that's true. So here's the solution. Since the polynomial has even degree and the leading coefficient is positive, this means that the polynomial goes to positive infinity in both cases as x goes to positive or negative infinity. Thus there has to be an absolute minimum, but no absolute maximum. From theorem 6.1.4, applied to the real line, the absolute minimum must occur at a critical point of the polynomial. Now polynomials are differentiable. Since p is differentiable, all critical points are stationary points, so we can find them by solving the equation p prime of x equals 0. So we take the derivative, and we get 12x cubed plus 12x squared. Factor out the common factor of 12x squared, and we get two solutions, x equals 0 and x equals -1. We evaluate both of those stationary points. When we plug in 0, we get 0. When we plug in -1, we get -1. and therefore we conclude that the polynomial has an absolute minimum of -1, and that occurs at x equals -1. Okay, let's talk about what kind of conclusions we can make now. What if we have a finite interval from a to b and it's an open interval? Well, as x approaches a from the right, if the limit is positive infinity, and as x approaches b from the left, if the limit is also positive infinity, what can we conclude? We can conclude that f has an absolute minimum but no absolute maximum on that open interval. The graph would look something like this. Okay, now let's go back to that same finite open interval. Let's approach a from the right and b from the left. In both cases, we get negative infinity. What can we conclude? Well, since the end behavior is negative infinity in both cases, we can conclude that f has an absolute maximum but no absolute minimum on the open interval from a to b. The graph might look something like this. Now let's switch things up. We're on the finite open interval from a to b. If we approach a from the right and get negative infinity, approach b from the left and get positive infinity, what can we conclude? Well, we can conclude that f has neither an absolute max nor an absolute minimum on the open interval. That does not mean that it might not have a relative max or min, just that it does not have an absolute max or min. The graph may look something like this. And switching it up one more time. Now if we approach a from the right and get an end behavior of positive infinity, approach b from the left and get an end behavior of negative infinity, the conclusion is quite logical. F has neither an absolute max nor an absolute minimum on the open interval a to b. Again, that does not negate the possibility of having a relative max or min, just that there cannot be an absolute max or min. The graph may look something like this. Here's the solution. We take the limit in both directions towards the endpoints, 0 from the right, 1 from the left. And we get end behavior that's exactly the same, both negative infinity. Now, because the function's continuous on the open interval from 0 to 1, this means that there has to be an absolute maximum. So what we do is we take the derivative. And when we take the derivative, we get f prime of x is equal to negative 2x minus 1 over x squared minus x quantity squared. Now, notice we have a quotient. The only thing we have to do is set the numerator equal to 0, and that's when we can figure out where the critical point is. So we end up getting x equals 1/2. Plugging in 1/2 into the function gives us an absolute maximum of -4. So this function has an absolute maximum at -4, and the end behavior is the same at both ends, because it turns out that 0 and 1 are both vertical asymptotes of the function. Next, let's talk about what the consequences are when a function has only one relative extremum. If a continuous function has only one relative extremum on a finite interval, or an infinite interval we'll call I, then that relative extremum must of necessity also be an absolute extremum. To understand why this is the case, suppose that f has a relative maximum at some point x0 on the interval I, and that there are no other relative extrema on f of the function on the interval. If f of x0 is not the absolute maximum of f on I, then the graph of f has to make an upward turn somewhere on the interval to rise above that point. However, this can't happen, because in the process of making an upward turn, it would produce a second relative extremum on the interval. Thus, f of x0 has to be the absolute maximum as well as the relative maximum. This idea is captured in the following theorem, and they're going to state that with a proof in the textbook. I'm not going to use the proof in the lesson, but let's look at a specific example first before we move on to the theorem. So exactly what is this idea we're trying to get across about one relative extremum? Well, let's consider the following function, and let's say that the relative maximum here is at x0. So since this is a relative maximum, it has to begin to go downwards. But if it has a turning point, that would cause another relative extremum, in this case a relative minimum. And that violates what we're saying. We're saying that the function has only one relative extremum. Therefore, this point can't exist, because if the function turned, that would create a second one. So in reality, this keeps going down and down and down, which makes this not just a relative maximum, but an absolute maximum. And that's the idea that we're trying to get across here. If a function has only one relative extremum, then that relative extremum has to be absolute. Because if it's not, then the function has to turn again somewhere, which would create another relative extremum, and that would deny what we're trying to put forward here. So that's the idea that we're trying to get across. Theorem. Suppose that f is continuous and has exactly one relative extremum on the interval I, say at some point x0. Then A, if f has a relative minimum at x0, then f of x0 has to be the absolute minimum. B, if f has a relative maximum at x0, then f of x0 has to be the absolute maximum of the function on the interval. Find all the absolute extrema of the function f of x equals x cubed minus 3x squared plus 4 on both intervals. First, the whole real line. Second, the line from 0 to positive infinity. Well, this function is a polynomial, and we've already talked about polynomials. This is an odd degree, which means that the end behavior is different. The leading coefficient is positive 1. That means that as x goes to negative infinity, the function goes to negative infinity, and as x goes to positive infinity, the function goes to positive infinity. Well, what does that mean? Well, since it's an odd degree polynomial, it follows that there are no absolute extrema on the open interval from negative infinity to infinity, the infinite real line. Okay, how about the infinite interval from 0 to positive infinity? Solution. Well, this goes from 0 to infinity. So if we take the limit, as x goes to infinity, we get positive infinity. We know that f cannot have an absolute maximum on the interval from 0 to infinity. However, the limit, as x goes to 0 from the right, is 4, and that's not infinite. So there is a possibility that f may have an absolute minimum on this interval. In this case, it would have to occur at a stationary point, which suggests that we look for solutions of the equation f prime of x equals 0. We take the derivative, we get 3x squared minus 6x, factor out the 3x, we get 0 and 2 as two possible stationary points. So f has a stationary point at 0 and 2. However, x equals 0 falls outside the interval because it's an open interval. 0 is not included. So the only stationary point that we can test is 2, and that lies inside the interval from 0 to infinity. So the theorem of 6.1.5 is applicable here. Let's do something we haven't done yet. Let's take the second derivative, which is all about concavity. Taking the second derivative, we get 6x minus 6. F prime of 2 is equal to 6, and that's positive. And if it's positive, that means it's concave upward. So what we have here is a relative minimum, because we have concave up, and it occurs at x equals 2 by the second derivative test. Thus, f of x has an absolute minimum at x equals 2 because it's the only relative minimum on the interval. And this absolute minimum is f of 2, turns out to be 0 itself. Finally, let's talk about absolute extrema and parametric curves. Suppose that a curve C is given parametrically by the equations x is a function of t, y is a function of t, and t is in the finite closed interval from a to b, where f and g are continuous on the finite closed interval from a to b. It follows from the extreme value theorem that f of t and g of t have absolute maxima and absolute minima for some values t between a and b. This means that a particle moving along the curve cannot move away from the origin indefinitely. There must be a smallest and largest x-coordinate and a smallest and largest y-coordinate. Geometrically, the entire curve is contained within a box determined by these smallest and largest coordinates. So let's go ahead and look at an example of this. Suppose that the equations of motion for a paper airplane during its first 10 seconds of flight are the following. X is a function t minus 3 sine t, y is a function 4 minus 3 cosine t, and so t is in the interval from 0 to 10, finite closed. What are the highest and the lowest points in the trajectory, and when is the plane at those points? Parametric equations can be a little bit difficult, so what we do is we graphically inspect the curve first, and we get something that looks like this. Now, what do maximums and minimums look like according to a parametric curve? That's the question. Let's begin our solution. The trajectory of this picture is showing things in more detail. We want to find the absolute max and minimum values of y, okay, for y over the time interval from 0 to 10, and the values of t for which these absolute extrema occur. The absolute extrema must occur either at the endpoints of the closed interval or at stationary points in the open interval from 0 to 10. To find those stationary points, we must solve the equation dy dt equals 0. And when we do that, we get 3 sine t equals 0. So we need to find values of t from 0 to 10, we're talking about radians now, where we get 3 sine t is going to end up becoming 0. Thus, there are stationary points in the interval from 0 to 10, at t equals pi, 2 pi, 3 pi, so on and so forth. Evaluating y equals 4 minus 3 cosine t at the endpoints and the stationary points yields the following 5 possibilities. The first one, plugging in 0, we get 1. Plugging in pi, we get 7. Plugging in 2 pi, we get 1. Plugging in 3 pi, we get 7. and plugging in 10, which is the endpoint, we get an approximation, 6.517. Thus, the high point of y equals 7 is reached at 2 different times in the interval. Now remember, 3 pi is less than 10, so it's in the interval. So the two values where the path of the airplane reaches its maximum is at t equals pi seconds and t equals 3 pi seconds. And a low point of y equals 1 is reached at t equals 0 and t equals 2 pi. And that's consistent with the figure that we just had. In lesson 6.1, we've looked at a lot. We've looked at absolute maxima, absolute minima, relative maxima, relative minima, and what it takes and the different theorems that we can use, the different conditions that we can look at to see when we have them and when we don't. Next thing, we're going to head off to the homework, do some odd problems, and then, as I coach you through the odd problems, you're going to do the even problems, and you're going to get comfortable and become a master at finding absolute maxima and absolute minima. God bless you, wherever you are today.
Praise Father, Son,